I'd like to please ask you to stay on after our speaker today to chat with each other. A significant function of Probus is to provide a forum for fellowship, and we've tried to provide that opportunity in the form of virtual chat rooms. So recently, I read about a survey of how society is handling the pandemic. To me, it was no surprise that the senior segment of the population has shown the greatest resilience to the challenges of the pandemic. Seniors are more seasoned at waiting, and they can demonstrate patience that in a way is hard for many young people. We can stay the course. Nearly all seniors surveyed describe their general mood most days as upbeat or coping well, while acknowledging health concerns, caretaking responsibilities, and some loneliness. To say that older people are weathering the pandemic is not to minimize the serious problems that we all have to deal with. But age does give us perspective and the energy to adapt. And this virtual meeting is just one small example of us taking advantage of a modern tool to maintain the human contact. And that ends my sermon for today. So now on to the fun stuff. First of all, I want you to know that we have been in contact with the art gallery, and we are keeping an eye on when we can safely return to in-person meetings. And welcoming new members to Probus is always a highlight, and I believe Bob Shaw is here, and I'm going to ask Bob Dickinson, our membership chairman, to take over from here.
Thank you, Ken, and it's great to be able to introduce another new member today. Just for an update for the membership, our current membership is about 142 members. That's after we've gone through the 2021 renewal cycle, which is down probably 10 to 15 from a year ago. So just a gentle reminder that we are definitely still accepting new members, as you've seen over the last few months. And people are more than welcome to attend a Zoom session as a guest for a couple of months if they want to get to know it a little bit more about us. So if you know of someone, friend, family member that might be interested in Probus, don't hesitate to invite them to attend one of the next meetings.
Don't let the phone go.
And with that, I will. I'm going to ask
because I'm going to go on in about 2 minutes
to introduce Bob Shaw, our latest new member. So Howard, over to you.
Gentlemen, it is my very, very pleasurable honor to introduce a gentleman that I have known for a number of years. Robert Shaw, better known as Bob. Bob is 78 years young and has had a very varied and interesting career in life. It all started in music while attending Hill Park Secondary in Hamilton, Ontario, playing for Ron Wicken and at the Brant Inn. That'll bring back some memories. Being discovered by the Ron Metcalf Orchestra, which was traveling throughout the USA, changed Bob's plan to attend engineering at Ryerson. I guess it just got written right off. While traveling with Brenda Lee, Bob was honored with the title of Honorary Lieutenant Colonel of the Alabama State Militia. I'm not quite sure what that means, but you can ask him. Bob's married, and married life settled him down, and he became a master electrician. This led him into starting an access security company called Access Control Net, which under his direction became one of the largest Toronto providers, providing access to security for the Toronto Community Housing Center and the Workmen's Safety Insurance Bureau. This was across the entire province and region of Peel, just to name a few in Ontario. His passion for music continued while playing for Harry Walter, and he started a 22-piece band called Free Flight. This was his own, which led him to his nomination for a Juno Award in contemporary jazz in the year 2000.
Wow.
Now, retirement has found Bob a new passion, sailing. As a member, he keeps his boat at the Etopico Yacht Club and has regularly sailed to and from the Caribbean. And I've had to keep track of him on the internet and phones, touching base with him all the time he was traveling. Gentlemen, it is my distinct pleasure to introduce you to Robert Shaw.
Thanks,
All right,
Howard, and back over to you, Ken.
Okay, and thank you. Welcome. Thank you for that introduction of Bob, and welcome, Bob. And I'm looking forward to seeing you in person one of these months. So I'm going to hand over to Kevin now to introduce our speaker today.
Okay.
Thanks, Ken. I'm very happy to introduce our speaker today, Paul Delaney. First off, you have to know that Paul is an Aussie, Aussie by birth. I think they call them fair dinkum. He was born in South Australia, first degree in astrophysics at the National University in Canberra. And he's a proud wearer of the Outback hat. He's not wearing it today, I don't think, Paul. But we did see him wearing that hat in our newsletter. Very dashing, I must say. For the majority of his adult life, Paul has lived in Canada. He started out here doing a master's degree in astronomy at the University of Victoria. And that's where I believe he met his dear wife. Most of his career since then has been spent at York University. He's been a faculty member there for close on 35 years. All that time, he's been a tireless promoter of his life's passion, astronomy and space science. I'm just going to go through some highlights of his career. First off, Paul is a highly regarded professor and teacher. And I've looked this up. According to Rate My Professor, you can do it, go online. His students just love him. The word that keeps coming up, awesome, the adjective. He's a great teacher. He's also the director of the university's astronomical observatory, the campus observatory. And as you would expect, that comes equipped with some powerful telescopes and cameras to view the night skies. And I think behind Paul today, you may be able to see one of those telescopes. And what Paul has done, which is great, is he's encouraged through his career, he's encouraged lots of his students, as well as the public, to make use of that observatory. And in recognition of what, I came up with this, in recognition of these stellar outreach efforts. You get the pun? No, you don't. Okay. He's been honored with the Alan Carswell Chair for the Public Understanding of Astronomy. Isn't that a great title? Public Understanding of Astronomy. And we all need to know more about it. And that was an inaugural award, the first of its kind. And he's been, as you would expect, he's been the recipient of many, many awards. And the most notable one, I think, is the prestigious Sanford Fleming Medal for Excellence in Science Communication. He got that in 2010. And just by comparison, the 2013 winner of that award was none other than Chris Hadfield, the Canadian astronaut. So as you may have gathered by now, Paul loves expounding on the wonders of the universe. He's an expert. And this morning we are very delighted that he has offered to enlighten us about one of these wonders, Mars, a planet which has been in the news a lot lately. We heard about the successful landing of the Perseverance rover. Yeah, it's going to be a great talk. His presentation will provide a close-up look at the red planet. And he's also, I think, going to get into some discussion of whether life could have existed there or even on other planets. And that's a funny question. It's an interesting question because I didn't realize it, but the late, great David Bowie wrote a song Is there life on Mars? Okay, Paul, that's enough from me. Over to you.
Thank you very much for that wonderful introduction. Great to be with all of you this morning, and I hope I can live up to those wonderful words. Well, first things first, let me find my presentation. That's always the best way to start. And okay, unless I hear differently, I'm going to assume you can see the title slide and that we're ready to roll. So, as was indicated, Mars is certainly a planet which has held our attention, arguably for the last 150 years, ever since Jules Verne's commentaries about science fiction, Mars, H.G. Wells, the beginning of the 20th century. But in the age of space exploration, and by the way, we just went through our 60th anniversary of the first human in space. Yuri Gagarin flew on April 12, 1961, so we're 60 years young. Ever since those pioneering days of both crewed vehicles as well as automated spacecraft, Mars has been a destination. And so what I want to do today is give you a bit of a flavor about the past, the current exploration, and potentially the future activities that we will find on the Red Planet. And yes, we will touch base with a little bit of astrobiology as we go. First off, though, I do have to have my usual ad. Obviously, the campus is closed at this point in time, but that doesn't mean that you can't access the Alan I. Carswell Observatory. On Monday evenings at 9 o'clock, on Wednesday evenings at 7:30, the students of the observatory team are on the airwaves. You can go to observatory.info.yorku.ca or YouTube, whichever you prefer, to find the exact links. And you have the opportunity to both listen to our students, ask questions, and if the skies are clear, we will give access to the 1 meter telescope and transmit live imagery. And if it's cloudy, we're all aware of that in Toronto, then we have our past archival images to share with you. So there is no shortage of opportunity to engage with us. And the moment the campus is available again for the in-person activities, then I certainly do strongly recommend that you pop by and check out one of our telescopes, in particular, the 1 meter telescope. It's our pride and joy. It was installed a little over 2 years ago now, and it is truly a 21st century instrument. It sets on a dime. It's just gorgeous. 1 meter diameter aperture. It really pulls in the photons beautifully, gives you wonderful detail of nearby objects, planets in our solar system, as well as further afield. It's only one of our 3 permanently mounted telescopes, but it is definitely the best. Okay, end of ad. All right, we charge off looking at the planets in our own solar system. Many people want an answer to the question of why do we do this? Of course, we could explore these planets from afar with our telescopes, with our night instrumentation, our CCDs, our charge coupled devices, our cameras. We can do it from the ground, we can do it from orbit, but there is no real substitute for actually being there, to be able to go to those planets, to be able to orbit them so that your instrumentation has high resolution capabilities, to be able to go to the surface, to be able to dig into the ground, to analyze the composition and so on. Being there gives us insight into the whole process of planetary formation. And not just the planets in our own solar system. As you are all keenly aware, we have found over 7,000 exoplanets. Those are planets orbiting other stars. Because of the way we observe, those 7,000 exoplanets that we have found imply that every single star in our own Milky Way galaxy, and therefore by extension to the other galaxies in the universe, have planetary systems. Can't guarantee that to you, but statistically speaking, it is highly likely. And that means, because there are 200 billion stars in the Milky Way galaxy, there are probably many times more than 200 billion planets. Statistically, again, 10 to 15% of those planets are planets in what we call the habitable zone of their parent stars. That is to say, liquid water has the possibility of existing on the surface, assuming atmospheres and so on. So we're talking about tens of billions of potential Earths in the Milky Way galaxy. To be able to understand those planets, we need to have a very good grounding, a very thorough understanding of the planets in our own solar system. And so going to other planets in our solar system has really a very larger question that it is able to answer for us. And that is, are we alone? With the real estate that is out there, if we can understand how life formed on our own planet, and therefore by extension, how life could form on other planets, we may be able to answer this question sooner than later. So we're searching for life. That's really one of the fundamental core reasons why we go to Mars. Well, just a few sort of facts about Mars. It's a planet that is somewhat smaller than the Earth. We're talking about a planet that is approximately half the Earth's diameter. This quick view, this was taken some 30 years ago now, but Mars hasn't changed significantly in that period of time. You can immediately see that Mars is very different from Earth. An image of the Earth shows you clouds, shows you water, it shows you ice, whereas Mars is obviously a much drier desert-like planet. That has not always been the case, and first glances can be perhaps a touch deceiving. There are many similarities between Mars and Earth, and some of those include the volcanoes that we can find on Mars. We haven't seen any volcanic eruptions since the time of the telescope, and that's not a surprise to us, but there are many volcanoes that are still present there in a dormant state. We find huge rift valleys cutting across the equatorial plains of Mars, Valles Marineris. We are able to see clouds forming above those volcanoes that I mentioned. We can find ice caps, north and south polar ice caps. And of course, Mars, by virtue of its configuration, is able to experience seasons, not dissimilar to Earth's seasons. So we see the summer, fall, spring, winter type cadence on Mars, and we see the surface of the planet changing accordingly. So there are similarities between Earth and Mars, but the biggest difference is obviously the liquid water, which does not exist on the planet's surface today. There's certainly no shortage of ice, and as I hopefully will prove to you, no shortage of water in the past, but today, much drier, more desert-like conditions. Martian atmosphere is quite thin, even though I'm showing you clouds here, and they are water clouds, by the way. The clouds are much thinner than on Earth. The atmosphere on Mars is only about 1% as thick as the atmosphere here on Earth. And so the surface conditions much colder. And of course, even if there was air to breathe in that atmosphere, the atmosphere is primarily carbon dioxide. But even if there was air at 1%, it's far too thin for you and I to survive. But there is an atmosphere on Mars. And again, in the past, it was much thicker. Just to highlight one of those volcanoes that I mentioned, Olympus Mons. It is the largest volcano in the solar system. And as you can see by the scale there, we're talking about a volcano. It's pretty well a shield volcano. If you have ever been to Hawaii and had a look at their shield volcanoes, Olympus Mons is very, very similar, but on a much larger scale. We're talking about, give or take a bit, 500 to 600 kilometers across at its base. And the caldera, the cone there in the center of this image, stands about 20 to 25 kilometers above the mean elevation level on Mars. I could use the term sea level, but there's no sea there. The caldera stands about 25 kilometers above the mean datum on Mars. So this is huge. Now, if you look carefully, you can see some craters on the flanks, on the slopes of this volcano. If this volcano was truly extinct, then we would expect to see many more craters, holes, if you will, in the sides of the volcano. That does not appear to be the case, suggesting that Olympus Mons was, in fact, relatively recently, geologically speaking, active. Perhaps, 10, 20, 30 million years ago, but for a planet that's 4.5 billion years old, 10, 20, 30 million years is very recent. So there is still some life, geologic life, activity beneath the surface, but it is not nearly as active a planet as our own Earth. Well, as I indicated to you, going to these places is certainly much better than being able to just simply observe from afar. But getting to Mars, even though we've been doing that for the better part of 60 years, is not easy. And sort of this tongue-in-cheek, sort of like a football analogy, it was half time back around about the year 2000, and Mars was definitely up 24 to 15, which means basically that of the 39 spacecraft that we had sent to Mars, 24 of them had not reached the planet or had transmitted next to no data. Only 15 of those 39 had been successful in transmitting data back to the Earth. Often referred to as the Mars curse or the Mars ghoul. Bottom line to it, it's hard to get to Mars. And we're talking about both flybys, we're talking about orbiters, as well as landers. Mars is a difficult place to go. Indeed, any planet in our solar system poses significant challenges to a spacecraft. Well, I'm pleased to report that we've lifted our game since that 2000 slide, and Earth is now in front. We have managed to get to Mars now approximately 58 times, and 32 of those missions have been successful. And you can see here the flyby, orbiter, lander, and now rover contingents that represent those numbers. Generally speaking, since 2000, we have been very successful, particularly with the rovers on the surface of Mars. Quick summary of the recent few years. You can see 2016, 2018, and 2021. Those last 3 missions went into orbit this year, February of this year. You might notice that there sort of appears to be a 2-year or so gap between the numbers that I'm quoting here. Celestial mechanics. Mars moves around the sun, as does the Earth, but it moves around at approximately twice the orbital period of Earth, 687 days, if you want to be very specific. What this means is that because of our relatively feeble technology, we cannot get to Mars just at any old time of the year. We have to wait for the 2 planets, Earth and Mars, to be in the right configuration such that the orbit from the spacecraft, as it moves away from Earth, intersects the Mars orbit at just the right moment when Mars happens to be there. It is an elliptical orbit. The spacecraft basically becomes a satellite of the sun, and that type of cadence only happens every 26 months. And so we fly to Mars every 2 years and change. Now, as I said, since 2000, we've been pretty good at getting to Mars successfully. But just to underscore the fact that it's not always easy, I point to the image on the right. It's the Schiaparelli spacecraft, which converted itself into a crater on the surface of Mars in 2016. It was a European Space Agency, Russian Space Federation joint mission that went to Mars that year. The orbiter, the Trace Gas Orbiter, TGO, is still in orbit, so it's been very successful. But unfortunately, the landing craft, which was basically a Russian Space Federation vehicle, turned itself off during descent. It survived atmospheric entry, re-entry into the Martian atmosphere. It had fired up its retro landing thrusters. The radar on board this vehicle was looking around. Apparently, what happened is that the radar concluded that, we're on the ground. And in the process of doing that, turned off the engines. Unfortunately, it's on the ground was 3 kilometers in altitude, and the vehicle then plummeted to the ground and exploded. It was a significant loss to the Russian Federation, Space Federation, but nonetheless, it underscores the importance of going to Mars carefully, thoroughly, and to get back on the horse, so as to speak, to do it all again in the near future. And the European Space Agency and the Russian Space Federation plan to be on the surface of Mars with the Rosalind Franklin rover in 2022. So going to Mars is tough. That is the bottom line. But in February of this year, the United Arab Emirates HOPE vehicle went into orbit, their first space mission, let alone a first space mission to Mars. The Tianwen vehicle, that is from China, is in orbit, and it will put a rover on the surface in May of this year. And the Perseverance rover is from NASA and is the cousin to a vehicle called Curiosity that landed in 2012. So that's the most recent. just to step back a little bit, we've been on the surface of Mars in one way, shape, or another since 1976. And most of this audience will probably remember the Viking missions of July, August 1976. I can say that because when I talk to my students, they all look at me like I am a terrible fossil if I talk about anything that is pre-2000. So it's really nice to talk to you guys. Anyway, so Viking, 1976. This was the first time we were successfully on the surface of Mars, transmitting images. The right-hand image there, the lower right-hand image of the lander's foot, and then the top left-hand image, the first image from the surface in color. And as you can see, it's a distinct rusty brown color. Its surface appearance is because of the amount of iron which is in the soil. And of course, there's a fair amount of water. It's a highly oxidizing environment, so there's a lot of iron oxide, and that is the reddish hue that you see. The atmosphere is not blue. There's not enough atmosphere there to create what we call Rayleigh scattering. That's why the Earth's sky is blue. But it does pick up, the winds on Mars do pick up a lot of the surface soil and deposit it, suspend it in the atmosphere. And so the orange hue that we see in the sky is in large measure a result of suspended dust from the surface of Mars itself. Since those earliest days, we've been examining the surface with increasing detail, and the case for water has been building. Now, initially, of course, it was orbital surveillance, looking at the erosion features, the geologic imprints on the planetary surface that suggested that flowing water was once a part of the Mars landscape. And you can see the images there on the left. The image on the right is a more recent animated GIF that basically is looking at one patch of the Martian soil throughout the course of the day. And you can see fairly clearly that the appearance changes. And the interpretation, rightly or wrongly, because it's still being hotly debated, is that as the heat of the day warms up the surface, then some of the subsurface ice is able to turn briefly into a liquid brine. There is a lot of salt on the surface. And of course, we in Canada know full well that if you put salt on the ground, you generally can lower the freezing point of water, keeps ice from forming on our roads. The salty brine, which we believe is able to manifest itself mid-afternoon on Mars, is showing itself here as sort of a darkening, a wetting of the surface. It can't last for very long. We certainly can't have liquid water standing on the surface of Mars, far too low an atmospheric pressure, but briefly, we think we can see evidence of this sort of salty brine manifesting itself in the mid-afternoon, warm summer afternoon on Mars. Warm, by the way, on Mars, if it does get to -20, we're doing very well. Certainly, you can get to 0, but generally speaking, we're talking about minus a few degrees at best on the surface of Mars. As I said, the symbols for water, or the signatures for water, have been debated for the last 30 to 40 years. And the best way to answer the question categorically is to actually go down to the surface and examine the surface, look for ice deposits and so on, look for the signatures of frozen water, at least in the subsurface environment. Enter the era of rovers, and this is 1997 now, the Pathfinder and Sojourner. To give you some scale there, the Sojourner rover there, the top left-hand image, is about the size of a microwave oven. So think of your microwave oven on wheels, and it was able to scoot around the surface of Mars for about 3 months in 1997. It never ventured very far, but it was able to go up to and examine carefully targets of interest, rocks in the immediate area. And this was a huge improvement over the Viking vehicles, which of course could only reach out with its robotic arm about 2 meters away from the vehicle. So most of the analysis that could be performed by Viking was done in the immediate vicinity of the lander, whereas rovers, they can become sort of geologists on the move, and they are able to go up to targets of opportunity that are potentially considerably farther from the landing site. And so 1997 marked a huge change in our ability to examine the surface of Mars. The rocks that we found there, very much the sorts of rocks that you would find here on Earth, basically basaltic type igneous rocks, indicating, of course, a volcanic origin, and, as we will soon see, sedimentary rocks as well. 2003 represented the landing of Spirit and Opportunity. Now, these are rovers that are about the size of a golf cart. You can see them in the top left-hand corner. And like Pathfinder, they landed on the surface through basically airbag deployment. They were sufficiently light. Spirit and Opportunity were about 250 kilograms, but that allowed for airbag deployment. So the vehicle basically came through the atmosphere on Mars. The heat shield protected it. And then under parachute canopy, the vehicle would drift towards the ground. And then when it was within about 10 to 20 meters of the ground, the airbags would deploy around the spacecraft, and literally the parachute would drop this, cluster of airbags, and the vehicle would sort of bounce its way to a halt on the surface and then roll out to commence its journey. When we first heard about this type of deployment onto the surface of Mars in the 1990s, most of us sort of smiled and said, really? But it proved its worth. Pathfinder, Spirit, and Opportunity all landed very safely and very successfully that way. In the case of Opportunity, the moment it opened its camera eyes, it realized it had rolled into a very shallow crater, Eagle Crater, in fact. And it looked out at sedimentary rock layers. Sedimentary rock layers, of course, are put down in the presence of flowing water. And so literally within a week of Opportunity arriving on the surface of Mars, it was able to roll over to the sedimentary rock layers and do a chemical geologic analysis of the materials in those sedimentary rock layers, verifying the fact that those rock layers, the minerals within, were in fact placed there courtesy of flowing water. There are signatures in geology which cannot be replicated in any other way other than water transport, and that's the sort of sedimentary rock layers that were in Eagle Crater. And so all of the suggestions that we had from orbit for the preceding decades were verified from the ground with Opportunity. Mars had water in the past. It doesn't have liquid water on the surface today, but it certainly had liquid water in the past, both flowing in the form of streams as well as in the form of standing water like lakes. Opportunity was able to cruise around the surface for nearly 45 kilometers over 14 years. Not bad for a 90-day mission. That was what the guarantee basically said for Spirit and Opportunity. We should be able to achieve the majority of the science activities, the objectives, within 90 days. And Opportunity rolled around the surface for literally 14 years. The top speed of these vehicles, by the way, is only 100 meters a day because, of course, they're acting autonomously. They've got to be very careful. You don't want them to sort of run into a rock at speed. You certainly don't want to bury them inside a crater and so on. So it's a very slow process. But as you can see by the map here, it visited many, many craters, and its final destination, Endeavour Crater, there was a very, very large crater that it was quietly circumnavigating when we finally lost it. It succumbed to a dust storm on the surface of Mars, which covered the solar panels in dust, and without solar panels, without power, the vehicle basically froze in place. So the vehicles that we have put on the surface in the recent decades have told us that Mars was once a very wet environment. Well, the question that you're all sitting there asking is what happened? And could it happen on Earth potentially? Well, the answer is it can't happen on Earth. But what did happen on Mars, we now do well understand. Back in the earliest moments of the solar system's formation, 4.5 billion years ago, all of the planets, the terrestrial planets in particular, but it applies to the giant planets in the outer solar system as well, all of them formed basically by collision and accretion. There's a lot of leftover debris in a flattened pancake type disk that was the solar nebula. And the planets were forming by the attraction, the accretion, the bombardment of these planetesimals with the leftover material from the solar system's solar nebula. Earth found itself at about 12,500 kilometers. Mars found itself at about a little under 7,000 kilometers. Size really does matter in this regard because these objects were molten and very, very hot. And as the sun fired up its nuclear furnace and cleared away the leftover debris from the solar nebula, the planets began to cool. They cool, obviously, from the outside in. And so the crust forms, and then quietly, as energy is radiated away from these molten spheres, solidification takes place. And in the process of this solidification, we also get what we call differentiation. Differentiation is basically the process where the more massive, the denser materials sink towards the gravitational center of the planet. And we create layers. In the case of the Earth, you've got cores, both inner and outer cores, mantles, and crusts. Mars does the same thing. But because Mars is so much smaller, the heat loss is faster. And even though you are getting a solidification of the outer layers first, the ability for Mars to retain internal heat dissipates very quickly because those rock layers, which on Earth are many thousands of kilometers thick, on Mars are considerably thinner. And so the ability for the rock to insulate and keep the internal heat in Mars is much less. So Mars begins the cooling process. By about 4 billion years ago, Mars's surface was probably somewhat idyllic. Probably had an atmosphere, courtesy of what we call outgassing, of about 2/3 Earth's atmospheric pressure today. The surface was now quite cool, and therefore liquid water was able to form on the surface. The outgassing process certainly generates a lot of water vapor in the atmosphere. There is also what we call volatiles being transported from the outer solar system by comets and asteroids. They impact the planets of the inner solar system. And so there was a sizable amount of water vapor which was able to cool onto the surface of Mars into the form of liquid water. At the same time period on Earth, we were still quite warm because we were a much larger planet. And therefore, our interior was still quite hot. And while the surface of the Earth was becoming hospitable, at that same moment in time, I say about 4 billion years ago, where Mars was particularly hospitable, Earth was still a little on the warm side. Life on our planet, the first signatures of it, occurred about 3.8 billion years ago when our surface had cooled sufficiently to allow liquid water to exist in significant amounts. That was probably 200 to 300 million years after the same situation on Mars had occurred. Mars' interior was still relatively molten at that point. The differentiation process had allowed a magnetic field to envelop the planet. The magnetic field arises from moving electric charge in the core, or in fact, to be specific, the liquid outer core of Mars. And because Mars spins on its axis once every 24.5 hours, give or take, then there was a significant magnetic field that surrounded the Martian atmosphere. And this is important because the sun has what we call the solar wind. Basically, there is a stream of charged particles flooding from the sun, which acts a little bit like sandpaper. And in the absence of a magnetic field, that solar wind erodes away a planetary atmosphere. Early on, 4 billion years ago, Mars had it all. But unfortunately, because its planetary size was so small, by about 3.5 billion years ago, the interior, the liquid molten interior, had solidified. And in that process, took away Mars's magnetic field. In the process of taking away the magnetic field, the solar wind begins to act like sandpaper on the Martian atmosphere, depleting the atmosphere. As the atmosphere diminished, so too was liquid water forced into a vapor or a frozen state. And so if it vaporized, now water vapor in the atmosphere is subject to what we call photodisintegration. The rays of sunlight basically are able to break up water molecules, and the resulting oxygen and hydrogen escape into space. This process continues, and by 3 billion years ago, the Martian surface became pretty well desert-like as we see it today. Water vapor have been lost through the atmosphere. Some of the water, however, did freeze into the surface. As a consequence, whatever the hospitable environment was at 4 billion years ago no longer existed by 3 billion years ago. One of NASA's current spacecraft, MAVEN, that is in orbit, is actually able to look at the current atmospheric state on Mars, and we can still see the Martian atmosphere leaking away into space. And so when we do the arithmetic associated with the gaseous loss that Mars is experiencing today, and we trace it back, we come back to about 3 billion years ago when the atmosphere really did reach its sort of current situation. And that coincides with the loss of the magnetic field on Mars. So Mars was once a whole lot more Earth-like, but not today. We can see the ice fields when we use radar, ground penetrating radar. We can see huge ice sheets beneath the polar ice caps. The polar ice caps are made up of both water ice and carbon dioxide, dry ice, if you will. The CO2 is the permanent cap. The water cap varies during the seasons. At the height of summer, most of the water vapor, most of the ice is in the form of water vapor in the atmosphere. And of course, in the wintertime, when temperatures are much colder, the water vapor freezes out into the form of ice. And we can see this sort of layered ice structures, particularly in the North Polar regions. It's one thing to be able to do ground penetrating radar and assume that it's water, because what we're really actually detecting is hydrogen. What we want to do is to be able to go down to the surface and again, verify that what we are seeing from orbit is in fact water. 2008, the Phoenix mission, and the probe went down to a region at 70 degrees north latitude. Most of the probes that we send to Mars, we leave in the equatorial region so that their solar power is able to maintain the operation of the vehicle for long periods of time. Like on Earth, when you get too far north or too far south, there are periods of time during the year where the sun doesn't come across the horizon. And for a solar-powered spacecraft, that spells death. Well, the Phoenix vehicle went there knowing full well that it only had a 5-month or so mission lifetime before the sun just didn't get up above the horizon. But it was so important for us to examine these northerly latitudes, the sacrifice was felt well worth it. The vehicle landed, and the very first thing it did is it looked at the ground around it, and it found ice. The retrothrusters have basically cleared away the surface soil, what we call the Martian regolith, and exposed the ice sheets that we expected to find beneath the vehicle. And so literally, again, very much like Opportunity, Phoenix was able to successfully muster some of its required science goals within days of landing. The vehicle had a robotic arm. We examined that surface ice, and in fact, its pH value, its alkalinity, is well within the bounds where you melt it, you could drink it. And so again, there was important information that we were able to verify on the ground based upon preliminary orbital observations. The Phoenix mission had a meteorological package on board that was actually made here in Toronto at a company by the name of Optech. And apart from looking at wind speeds and temperatures and atmospheric pressure, it carried with it a LiDAR, which is basically a laser radar. And that LiDAR instrument basically pulsed laser light into the atmosphere and looked at the reflection of that laser light off the various airborne gases. And this gave us insight to the structure of the Martian atmosphere as well as its composition. One of the really very neat observations it made back on Sol 99 was looking at some of the Martian clouds. And as I showed you earlier, you do actually have cloud formation in the Martian atmosphere. It doesn't rain, but it does snow. And here you can see the development of the cloud and how at around about, sort of 6 o'clock, 5 and 6 o'clock, it began to snow. You can see the streamers. This is ice streamers, snow streamers coming from the cloud at about 4 kilometers altitude, heading towards the ground. That snow doesn't accumulate in any significant way, but there was detection of snow in the Martian atmosphere, and it seems highly fitting that it was a Canadian instrument that actually did that detection. So we've had 3 generations of rovers on the surface. I've introduced you already to the Pathfinder Sojourner, the little microwave oven there in the lower left. We've introduced you to Spirit and Opportunity, the Mars exploration rovers, about the size of a golf cart there on the top left. Now let me talk to you about Curiosity and Perseverance. These are vehicles that nearly weigh a ton and are actually about the size of a small SUV. So they are very significant vehicles with about 100 kilograms of instrumentation, science instrumentation, and perhaps more importantly, they are not solar powered. They utilize what we call the decay of plutonium, a radioisotope thermoelectric generator. So as the atoms decay, giving off heat, we convert that to electricity, which powers the vehicles. 2 of those vehicles, Curiosity and Perseverance, they did not land through airbag deployment. Rather, they experienced what we refer to as the 7 minutes of terror. These vehicles hit the upper atmosphere of Mars at about 21,000 kilometers an hour, and then they have 7 minutes to slow down safely to the surface for a nice quiet landing. So they utilize heat shields to wash away a lot of that energy in the form of speed. They deploy a parachute, which at 1,000 kilometers an hour is actually really quite the process. And then they lower themselves to the ground with retro thrusters, rocket engines, and then winch the spacecraft to the ground with what we call the sky crane. This whole process happens completely autonomously because, of course, Mars is always several light minutes away from Earth. And so you can't control the vehicle in real time. This is all an autopilot type process. Well, both Curiosity and Perseverance have executed this sky crane maneuver flawlessly. Perseverance did it in February of this year. You can see the lower left image there, the vehicle floating down under parachute canopy in the Martian atmosphere. You can see the sky crane winching the vehicle down to the surface there in the top left. And one of the first images from the vehicle Perseverance on the ground. It's in Jezero Crater. Jezero Crater is an ancient lake bed. It had a river that flowed into it back 3.5 billion years ago, and it contained water for, well, we estimate something like 500 million years. One of the prime mission objectives to Perseverance is to search for signs of life. And as I've explained to you, the time that life could have existed on the surface of Mars was 3.5 to 4 billion years or so ago. So Jezero Crater represents one of the best locations for searching for life. Curiosity, as a matter of interest, is in another lake bed by the name of Gale Crater as well. Can life survive this time process? It's obviously very unclear. We have found a very active chemistry in the soil of Mars. We have found sort of chemicals called perchlorates, which could drive the energy needs of ancient Martian life. We know that there is subsurface ice. There is great speculation that there is subsurface water, buried artesian water wells, and so on. Whether or not that environment beneath the surface, where, of course, the life is potentially protected from the harsh radiation environment on the surface, whether or not life has been able to sustain itself over the last 3.5 to 4 billion years, we do not know. But following the water, following the probability that if life could have developed, they would have developed in and around these lake beds, that's what NASA is following at this point in time. And so Jezero Crater, Gale Crater are the best destinations for the search for life. That's one of the primary objectives of Perseverance. It's also caching a lot of rock samples because this is a very capable vehicle. It's drilling into rocks and creating rock samples that will be returned to Earth back in and around 2030. A joint European Space Agency NASA mission will pick up these cached rocks from Perseverance and bring them back to Earth. Perhaps one of the most exciting engineering tests that is being performed on the surface of Mars at the moment is our little helicopter Ingenuity. It was supposed to fly last Sunday. It will probably fly early next week. They've had some technical issues, well, actually programming issues that they want to resolve. But Ingenuity is about a 2-kilogram drone helicopter that is now sitting on the surface of Mars about 200 meters from the Perseverance rover. Perseverance brought Ingenuity to the surface, dropped it onto the surface of Jezero crater, backed away. This is a solar-powered vehicle. So it charges itself during the day, it keeps itself warm during the night with the batteries. And if all goes well, it will take flight next week. 30-second, 45-second flight to a height of about 3 meters or thereabouts. Doesn't sound much, but it's basically proving that we can fly in a very, very reduced atmospheric environment. And so it is hoped that Ingenuity will pave the way, not this mission, but pave the way this mission to bringing more Ingenuity-type helicopters to the surface of Mars, now laden with instruments. That way, of course, Ingenuity could fly in advance of a rover, figuring out where the best directions were to go, looking for interesting samples, and potentially going up onto rocks that rovers cannot access. And so while Ingenuity at the moment is nothing more than, can we do it? If it is successful, and we've got every reason to believe that it will be, then we should be able to fly these types of surveillance drones ahead of rovers in the future. So keep your eye on the flight of Ingenuity, slated for early next week. Last but not least, of course, is the question of, can we get there with humans? Ever since the late 1960s, NASA, US presidents have said that we are going to be on the surface of Mars, boots on Mars, within 20 years. Well, it's 2021 and we're still not there. But there is signs of hope, shall I say, that we could be on the surface of Mars with people in the 2030s. And that's mainly because NASA now has a lot of allies, both around the world in the form of the European Space Agency, the Russian Space Federation, the Japanese Space Agency, but also private groups like SpaceX, Blue Origin. They have all now developed a great deal of expertise as far as spaceflight, spacecraft are concerned. Certainly, if you listen to Elon Musk, he would like to be on the surface of Mars next week. But you know, I think the 2030s is a more reasonable expectation. The vehicles required to deliver payloads to Mars are again within our reach. The Saturn V was able to do it. However, SpaceX is developing what they call Starship and Super Heavy, which will be able to deliver significant payloads to the surface of Mars. And those payloads, of course, would include the required elements to survive on the surface of Mars, not to mention taking people to orbit and then down to the surface of Mars. So can we get to the surface of Mars within the next 10 to 15 years? We probably can, but it does require political will, and it does require the type of collaboration that we have seen on the International Space Station. Whether or not all of that can come to pass, ask me again in about 10 years, but I am quietly optimistic. On that note, let me stop and open up for questions, because we've covered a lot of material here about the history of Mars, and I dare say many of you have got lots of questions to ask. So let me stop screen sharing and say over to the moderators.
Okay, thanks, Paul. And so what we're going to do for asking questions, if you have a question, raise your hand. Gary will keep an eye out for you, and he'll give you the high sign. And please unmute yourself, ask the question, put yourself back on mute. Okay, go ahead, Gary.
Okay, just gonna let everybody know I can only see about 2/3 of the people, so I'm gonna have to keep switching screens. So if you got your hand up, just keep holding it up for a minute until I see you. And Chris Walker, do you want to go ahead, unmute yourself?
Yeah, fascinating presentation. It's beautifully done, extremely interesting. Huge amounts of money are being spent to get to Mars. What are the resources on Mars that people are after?
That's a good question, actually. certainly from NASA's perspective in the scientific community, it is more along the lines of what I mentioned earlier. We're trying to understand planetary formation. As long as we stay on Earth, we only have one sample point to understand the way planets form, the way atmospheres evolve, and so on. So going to Mars from a scientific perspective is very much centered on trying to understand the overall process of planetary formation. But we are searching for the signs of life, which obviously answers the question of whether or not life could be commonplace throughout our galaxy. At the moment, again, we have a sample of 1 point. Earth is the only place that we know of categorically that has life. And we have a great plethora of life here, including extremophiles and so on. Can some of that life be found on Mars? But in terms of the resources, there certainly is every reason to believe that Mars has an environment, a rocky environment that is very similar to our own rocky environment. So putting aside things like fossil fuels, because we've never seen large-scale life on Mars to generate those sorts of resources. But in terms of the precious metals, and I'm not just meaning gold here, I'm meaning things like the semiconductor materials that allow us to build our modern environment here. Those types of features we know exist on the surface of Mars. Whether or not you can mine it successfully and send it back to Earth, huge question. It's probably easier to mine asteroids, for example, where you don't have the same gravitational well to deal with, and where the asteroids come by Earth on a regular basis, what we call the near-Earth asteroids. So it's debatable whether or not you will be able to mine Mars, practically speaking, and send it back to Earth. I think it is more reasonable to simply say Mars has got its own self-sustaining environment where you can build up, a settlement there, that you can go there and inside pressurized bubbles, you've got to worry about radiation too. It's not easy, but you go there, you've got enough ice, you turn that into liquid water, you make sure that you've pressurized the dome, you can grow your own food there. You have to take, of course, along some microbes, and that opens up the other question of whether or not we really want to impregnate Mars with life from Earth. So there's a whole range of questions that are not just science questions, they're morality questions and so on that need to be asked with respect to going to Mars. But I think the main drivers at the moment are the notions of both the science and the settlement options. Elon Musk has often said he wants to see us as a multi-planetary species because, one of these days we may need a lifeboat. I'm not sure that I buy that particular argument, but we are explorers. You only have to look at human history to recognize the fact that going off and settling another location and then moving further out into the solar system, out into the galaxy, I really do think that is humanity's destiny. And so figuring that out on the surface of Mars is a viable first stop.
Thank you. Thank you.
Next question. Ray? You got to unmute yourself, Ray. You're still muted, Ray. Yeah.
I'm unmuted, I think.
Just like my students in the class. It's okay.
The question I had is, I grew up in an age when there was a lot of discussion about the canals on Mars. What is the current scientific explanation for those?
The canals on Mars were completely fictitious. They were canali. They were seen by an astronomer by the name of Schiaparelli in 1877. Basically, what he was seeing was surface changes. Mars, because of its dusty nature, the wind structures on Mars, does change its surface configuration on literally a seasonal basis. And so if you're carefully mapping out the surface of Mars with the eye, then you're subjected to what we call seeing conditions here on Earth. Sometimes it's easier to see through our atmosphere than at others. And on the Martian surface, the relocation of vast amounts of soil change the appearance, what we call the albedo, the shadings on Mars. Schiaparelli was a very good astronomer. He was very accurate in what he drew. But if you think back to the lines that he was drawing, he was just basically showing changes that were on the surface of Mars that were then interpreted by the media, and a colleague of mine in the astronomical circles, Percival Lovell, they were interpreted to be canals, as in irrigation ditches that were moving, quote, ice water from the polar regions to the more desert-like areas of the equator. Of course, there is no liquid water on the surface of Mars, so these canals couldn't have been irrigation ditches. But it didn't change the fact that Percival Lovell was absolutely convinced that they were these types of ditches, and therefore there had to be intelligence on Mars. And then, of course, H.G. Wells came into the picture, and the War of the Worlds, and so on and so on. So it just all snowballed into this almost belief that Mars had to have life. By the time we got to the 1960s and we sent spacecraft there and we knew what was happening on the surface and we began to understand the dust storms and so on, and the fact that the underlying bedrock was much darker in appearance than the overlying regolith, red soil, and so on, you know, by the 1960s, we better understood what was happening on Mars. And so the canals were really just, I don't want to say an optical illusion, because there are surface changes, but they were an illusion from the perspective of being irrigation ditches. If you do the calculation of how wide those irrigation ditches had to be, you know, Mars is sort of 6,700 kilometers wide. You're seeing conditions here on Earth about 1 arc second under the most ideal conditions. For a straight line to be visible on Mars and for it to be real, it would have to have been something like 300 kilometers wide. And I don't know of any irrigation ditch that's 300 kilometers wide here on Earth. So they are fictitious is the bottom line to us.
No.
Hey,
We
maybe
find-
one last question, Gary?
Yeah, Ken, how are we doing for time?
Yeah, maybe one last question, that'd be good.
Okay. I see Jim Jones has got his hand up. Jim, go ahead and unmute yourself.
Okay, thank you. You mentioned in towards the end of your talk that we couldn't do all of this without the help of partners such as the European Space Agency, the private companies, etc. What about the Chinese? Are they doing this in competition, or are they cooperating with others? What are they up to?
Oh, over a much larger coffee, we could have this conversation. At the moment, I think the short answer has to be competitively. It's unfortunate that most of the various space federations around the place have started to work very collaboratively. And I hold up the International Space Station as a really great example. It's 16 countries that are maintaining the operation of the ISS. The Lunar Gateway, the return to the moon with the Artemis project is also designed to be very, very collaborative. But the one player that is not involved in this, and it's political, is the Chinese. And so they have embarked on their own space program. They've gone to the moon. They've brought samples back from the moon. They have put space stations in orbit. They're planning to put a bigger space station in orbit. The Tianwen space vehicle is their first successful attempt to go to Mars. They're in orbit at the moment. They plan to put a rover on the ground. But in large measure, they are doing it solo. And so you've got to answer your question with it's a competitive process. And, the competitive process of the space race in the 60s, going to the moon with the Russians and so on and so forth, finally gave way to a more collaborative engagement between, Russia and NASA. But it took a long time for that to develop. So I suspect it's going to be a little while longer before China and the rest of the various space federations do get together. But at the moment, the answer really has to be it's a competition.
Okay.
Thank you.
Thank you, Paul. I found it interesting. There's always some symbolism in these space flights, and I read that the Ingenuity helicopter is actually carrying a small swatch of cloth from the Kitty Hawk, and to show the range of development over many, many years. But thank you very much on behalf of everybody today. Thank you for a very stimulating talk. And with our thanks, please feel free to leave our meeting with our thanks.
Thank you very much indeed. If there are any other questions, because we only got a few of them, there is an email address on my slide deck, pdelaney@yorku. Feel free for anybody to send us along any other questions.
Wonderful.
Okay. All right. Have a great meeting, guys. Thank you very much.
Okay, so that concludes the formal part of the meeting, and it's been recorded as you know, and it's going to be uploaded to YouTube within the next couple of days. And at this point, we're going to move into our chat rooms. And as I mentioned at the beginning, this is our attempt to provide a virtual form of fellowship. So please stick around. Bob's going to assign you to a room. I understand you'll need to agree to join and then take yourself off mute.
Ken, sorry
Yeah.
to interrupt. It's Kevin. Could you just mention next month's speaker before we go
Yeah.
into the room?
Yes, I was about to, Kevin.
Sorry.
Our next meeting is scheduled for May the 20th. And Dr. Dale.
Okay, hang on for a sec. Okay, good.
Sorry. Okay, so our next meeting is scheduled for May 20, and we're going to have Dr. Dale Kalina, who's going to tackle the topic of the pandemic, vaccines, and go-ahead protocols. And so I'm going to hand it over to Bob to divvy us up.